Hello guys, in this section we will explain the unit of the power and the power ratio in electromagnetic applications or fields. In many or in almost engineering sectors, fields, applications, power is measured by watts and power ratio like the efficiency, the gain, the losses, the transmission. It could be calculated and determined in a scale system. Okay, so for example, we say the efficiency is 90% or zero point 0.9, and the gain is, for example, 50% or zero point 0.5, and go on. In any electromagnetic application, and specifically in communication sector, the power in such applications or in such fields almost has very small values. So it could be maybe in order of millimeter watt or even smaller than that, maybe in micro watt. So according to that, according to make this value more significant in our calculations or modelings or determinations. So we would use the decibel system to measure the magnitude or the values or the levels of the power or the power ratios. So the decibel, as we know, sorry, the decibel is mean the logarithm multiplied by 10 for a significant ratio or a certain ratio. In scalar, we know, of course, if we need, for example, to calculate the gain, so the output power to the input power, this is the gain, okay, for example, or the transmission or the losses of any channel. So now if we need to convert this scale to decibel system, we need to take logarithm for this value and multiply it by 10, and the unit, it will be dB. The unit, which will be dB. If we need to measure power value, absolute power value, okay, for example, received power or transmitted power, so the ratio will be between the value of the power which we need to calculate it, okay, or sorry, measured in decibel, to the 1 milliwatt as a reference, and then also take the logarithm and multiply by 10. So, and in such case, the unit will be dBm. Okay, and there are many forms to measure the power in decibel system, like dBW, and the reference will be 1 watt, okay, and dBi for measure the gain of the antenna by compared with the isotropic, and go on. And I think we will explain many of these forms maybe in next semester with the antenna lectures. Okay, so that's if we measured the ratio between the power. If the ratios are calculated between potentials or fields, so the formula will be 20 multiplied by logarithm ratio between the two potential or two fields, because we know the power is proportional with square of the potential, or the power proportional with the square of the electric field or magnetic field, and the units will be keep as a dB. Keep the table between the scalar value of power ratio and its counterparts in decibel value. So when we have 1, that's mean the ratio is 1, so the output power is equal to the input power, or the output field is equal to the input field. So here we have 0 dB. So anything smaller than 1, that's mean we will get negative values in dB, and anything larger than 1, that's mean we will get positive value in dB. The attenuation rate here is calculated in decibel system. Okay, so the attenuation rate we know is represented by the ratio between the power at any position to the initial power or the maximum power, or here it's represented by the power density, the average power density. So the average power density at any position compared with the power density at the initial or the maximum power density. So this ratio is equal to the attenuation function in case of the power density. So here we have 2 because we are working with power density, and by solving this at the final we get attenuation rate, its unit dB per meter, equal to 8.68 multiplied by attenuation rate in a scalar, that's mean 1 per meter. So now any value of attenuation rate in a scalar, we could convert it to dB per meter by multiply it with 8.68. Okay. Same thing if we measure the attenuation rate for fields, that's mean fields at any position to the maximum field or field at the initial, and here we will multiply this ratio by 20 logarithm because the power is or the power density proportional to the with the square fields. Example 7.6. Here we have a submarine, okay, at a depth of sea or of ocean. This depth is 200 meter, okay, below the sea. Yeah, it's a sea, below the sea surface, sorry. And it has a wire antenna to receive signal transmission, signal operated in 1 kilohertz, its frequency. Determine the power density incident upon the submarine antenna and this wire antenna due to the electromagnetic wave of example 7.4. If you remember this example which we solved, and it talked about electromagnetic wave propagated in seawater. So now we will need to use the parameters which we got from this example from 7.4 and apply this parameter to use it as an electromagnetic wave, okay, received by wire antenna in a submarine, okay, which at a depth of 200 meters below the sea surface. Okay, so of course if we need to calculate the power density, we will need to use the formula of the power density for loosey media, because now we are talking about seawater. So for loosey media, the magnitude of the electric field squared, maximum electric field squared, divided by 2 divided by magnitude of intrinsic impedance, all this multiplied by the attenuation function, okay, and multiplied by cosine to the theta or the phase of the intrinsic impedance. So all these parameters will be taken from example 7.4. So magnitude has been calculated 4.44, okay, times 10 to minus 3, 4.44 millivolt per meter. The magnitude of the intrinsic impedance is 0.044, okay. The alpha, I think 1.26, something like that, yeah, or 0.126, sorry. And the phase between electric and magnetic field, it was 45 degree. So at the final now we will get this formula, and because now we need to calculate at a 200 meter where the supermarine it exists. So the power density will be 2.1 multiplied by 10 to power minus 26 watt per meter square. Okay.